Can you drop the video link? Because I can't hear any of the audio.
Oh, sorry. All right. Okay. Sorry, let me start over.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
Lee Sedol is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Well, look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, it's made a mistake.
He's got to pronounce a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
So I definitely recommend you guys to watch that movie. I'll send the link later, but it's a pretty good documentary of what happened in 2016. So before though, we can build an AI to take on the world champion, we need to develop skills and we need to learn about the basics of artificial intelligence and machine learning. And so that basics starts off with a neural network. And so before we talk about a neural network though, we're going to first define a few terms. What exactly is artificial intelligence? So by definition, artificial intelligence is any technique that enables computers to mimic human behavior. You guys may have played video games like Pac-Man or Mario, where the enemy tries to follow the player and tries to attack that player. That's considered artificial intelligence. It's a very simple one, and all it does is try to calculate the distance between the player and the enemy, but that's considered AI. Machine learning, on the other hand, is a subfield of AI. And this tries to learn things without being programmed to do it. One good example of this is spam detection for your email. And finally, deep learning is a subset of both machine learning and artificial intelligence. And this is where many of the breakthroughs have been occurring. These ideas aren't new. They've been there since the 1950s. But because we have a lot of data now, and our computers have gotten better. For example, we have better GPUs, we have better CPUs. And so we've been able to leverage that for deep learning. And this extracts meaningful patterns from data. And the basics of this uses neural networks. All right, so neural networks, the intuition behind them, they're loosely inspired by the human brain. In our brain, we have trillions of neurons, and each neuron is connected to other neurons and through nerves or connections. Now, based on some input that we get, some collection of our brain fires or doesn't fire, those neurons in our brains. And that's what dictates what we see and what we can categorize. So before, again, we talk about neural networks, I first want to talk about functions. And this is going to sound really trivial, but it is a good distinction. So pretty much you guys are probably aware that functions take an input X, they are mapped to some function f of X, and then they get some output Y. Now, any input we can give a function, it'll predict it. That's what kind of functions are. They apply some transformation. And we can also have as many inputs as we want. In this case, we have 2 in this example. But we can have as many inputs as we want. We could also have, in the case of neural networks, as many outputs as we want. And that the number of outputs depends on our case. What do we want to predict? However, many times in the world, we have our input, our X, we also have our output, our y. Many times we don't have our function, our f of x. And this is pretty bad because we need that function. We want to predict things that we don't have the data for, but can be generalized to new data. And this is where a neural network will come in. Neural networks are really good function approximators. What that means is that any function or given data and given the input and given the output, a neural network will try to predict what that function is. It will try to approximate the relationship between the input and the output. And so before we talk about actual neural networks, let's talk about linear regression. Linear regression is a form of machine learning. It is one algorithm used for machine learning. In linear regression, our formula is y is equal to mx plus b. Now, our m, you guys will probably be familiar, that's our slope. Our b is our y-intercept. And many times, like we have our data, and we want to predict a good function. There are times when our data is a linear relationship. What that means is that we have data. For example, let's say we want to predict housing prices. We want to predict how much is a house going to cost. So our input data might be the number of bedrooms it has. That's going to be related to the housing price. And so maybe our x-axis is going to be the number of bedrooms that our house has. Our y-axis is going to be the actual price of the house. And this is going to be our predicted value. So when we use this formula, once we figure out the slope and the y-intercept, and I'll explain how we do this later, we input some variable. For example, let's say, or we input the number of bedrooms. Let's say we have 3 bedrooms, and that's, let's say, right here. Then our price, our predicted value is going to be around here, and maybe that's $500,000, let's say. And so our goal is essentially to get a function that will be a good approximation of our data. And so in this case, this is linear data. So we can use linear regression. As you guys can see, this is pretty positively correlated. And this is exactly what a neural network is going to try to do, but more complex. And so, oh yeah, by the way, guys, if you guys have any questions, please feel free to interrupt. And okay, so we're not also limited to one input. For example, let's say we have the number of bedrooms. We also maybe have the number of bathrooms. And we think that that might be correlated with the price. Well, we can do that. We can set x of 1 to be our number of bedrooms we have, and x of 2 to be the number of bathrooms we have. And using this function, we will predict and we will find a good function that will approximate this data. Now, let's compare this to a neural network. This is a very basic neural network. This isn't gonna have much practical sense, but it is a good intuitive feeling for it. So in this case, we're gonna have 3 inputs. This is the same thing as our linear regression, where we have as many inputs as we want. We're next gonna have this weight. I'll explain what these arrows are. And we're gonna have some output, y. Now these weights are actually gonna be our slope. If you guys remember from our linear regression in the previous slide, those weights are gonna be exactly equal to our slope. And so it's our job to figure out what those weights are. And we use different algorithms that I'll explain later to figure out what exactly are these weights. And so let's look at the formula. I think this is a good intuitive feeling for it. And this is the formula essentially for it. Our prediction is gonna be equal to, ignore this part for now. I'll talk about what that is later. But it's gonna be equal to the summation of our weight, which is our slope, times our input plus the y-intercept. if we expand this formula, if you guys aren't familiar with summation, this just means that we add it all up together. And so if we expand this, ignoring this sigmoid that we see for now, I'll explain that later, we have our first weight times our input, plus our second weight times our input, plus the number of inputs we want. If we have 2 inputs, then we stop here. This is where we stop at, and we only have 2 weights and 2 inputs, plus our bias. Now, if you guys remember, this is excluding this sigmoid. This is exactly our linear regression equation. We have a weight times the input plus the other weight times the second input plus the bias. And so excluding this sigmoid, it's exactly our linear regression model. And so this is also a good diagram of what exactly is happening. So we have our inputs, which again, we can have as many inputs as we want. Those inputs are multiplied by the weights, which is our slope in the case of linear regression, and we add a bias to it. Then the activation is involved. I'm gonna explain what the activation is, and that's that sigmoid that I told you to not pay attention to. And with all that, it gets us our output. And so what exactly is the activations that I'm talking about? Those activations, they come in their functions essentially. They come in different forms, and the formulas don't really matter, but why do we have that? Why is our neural network not like our linear regression? Why do we even want, why don't we just use linear regression essentially? Well, because in the real world, we have nonlinear data. What does that mean? In the case of the linear regression model, you guys can see this is a linear relationship. It's a linear correlation. However, in the real world, and I'll show you guys an example of this. Can you guys see the new website? All right, so this is an example, if you guys look right here, of some data. As you guys can see, this is a spiral. And there's really no way a linear regression model could predict this. You know, maybe it could try to do this, maybe it could try to do that, but that's not a good prediction. That's not a good function approximation. What we want is a good function that will approximate like a spiral. And that's why we use a neural network. Neural networks are particularly good at doing this. Sorry. Yeah, so like I said, neural networks are pretty good at this. The reason they're good at this is because they have an activation function. That activation function is the sigmoid that I told you to forget about right here. It's this sigmoid. And that's the function that we want. That's what allows us to approximate to nonlinear data. For example, it allows us to approximate to spiral data. And these are common functions, ReLU, this is rectified linear, or tanh. These are common functions that I use. They all depend on what case scenario you're using. But using this, you apply it. So if we go back to our formula, we multiply the inputs by our slope, we add the bias, then we put that into that function. It could be ReLU, it could be sigmoid, but we put that into that function, and that's what approximates. That's what allows us to approximate to nonlinear data. And so this is another example. This is another good image of what a neural network looks like. As you guys can see, we have 3 inputs in this case. We have 2 outputs. Like I said, we can have as many outputs as we want. We can have as many inputs as we want. It all depends on our case scenario. However, what's different about this diagram is that we have this hidden layer. We're going to call that H. Now, this is also the biggest thing that differentiates neural networks from linear regression. It's the amount of layers they have. These layers are the deepness that comes with deep learning. We need these layers the reason we need these layers is because these layers allow us to approximate to complex functions. For example, let's say we have a data set of cats and dogs. We want to predict whether an image is a cat or a dog. Well, that's a pretty complex function. And we can't use linear regression, of course. And the previous diagram that I showed, that's too limited. So we need something that has more layers that allows us to have more complexity. And layers is what allows us to have this complexity. And so in this case, we have one layer, but we can have as many layers as we want. And I'll talk about how many layers is good and bad, but this is another diagram that shows us we have one input. We have 4 inputs in this case, actually, but one input layer. We then have 2 outputs, in that this is our last layer. We also have...
Are all the hidden layers just different functions plugged into each other, basically?
So they take up the same, if you remember the function for a neural network, right here, this function, they all take up that function. But instead, if you have more layers, basically instead of this X being your input data, this becomes another function. So this becomes your sigmoid function, essentially. And so it's a composite function. And as you have more layers, the more composite functions you have. Does that make sense?
Yeah.
All right. So yeah, in the real world though, we don't really have to worry about the equations. We use frameworks, we use programming languages, especially Python mostly, in order to, because this is basically all done for us. And for this example, I'll use TensorFlow, which is a open sourced library built by Google. And so it's not too important because next week we'll be actually implementing this. But just to give you an idea, we import our modules first, and then we set our model equal to a sequential model. All this means is that we go from 1 to 2, and it doesn't really matter, but it just means it's a feed forward. So it just goes from this layer to the next in a sequential manner. And finally, we have it in an array of dents. Each dent is one layer. So if this is let's say we only have one layer, we're only gonna have this one dense neuron, one dense layer. And this n is the amount of neurons that we want. If we want, so in this image, we have 1, 2, 3, 4, 5, 6 neurons. And so this case would be dents of 6. And that's what would be our first layer. Our second layer, this also has 6. So this would again be our dents of 6. And our third layer would have 3 layers. And so we would have a dents of 3. And we can have as many layers as we want, but I'll talk about why we don't want too many layers and too many neurons. And so we've been talking about what a neural network is, but how do we actually find those weights? Because those weights are what does the actual learning. Like that's what we actually learn by. It all depends on what those weights are. We don't know what those weights are initially. Actually, they're initialized at a random value. And so they're gonna give a prediction that is pretty bad. So to understand this, I'm kind of gonna give an analogy. So you guys probably remember in first grade or second grade, that where you guys started to learn how to add numbers. Your teacher would probably give you a bunch of data. They would probably give you 1 + 1 is equal to 2. That's our data, essentially. We have a 1, and our output, our expected value is a 2. Now, let's say when the test comes, you do the test and the problem is 1 + 3, and you answer 5. That's incorrect. It should be 4. So we have an error in that case. Our goal is to try to minimize this error. And when we minimize the error, we find the best weights possible in order to generalize our function. Because we want to find the best function possible But to find the best function possible, we need to find the best weights possible. And we try to do that by minimizing an error. And like I said, we predicted a 5 in the test case scenario. So the problem was a 1 plus 3. And the answer I got was 5, but the correct answer is 4. So the error between that is going to be 4 minus 5, which is -1 squared. So we're going to have a non-zero error. And this is important because we want to try to find an error that is as close to 0 as possible. That's how we know that we're going to find the best weights that we can. And in practice, we don't really find the best weights, but we find a pretty good approximation to those weights, or to a pretty good approximation to a good function. And so we're going to use, yeah, we have two cases as in this. We have a regression case and we have a classification case. If you guys aren't familiar, regression is essentially the example of the house prices. The house prices, I want to predict maybe it's going to be $500,000. Maybe it's going to be $1 million. That's a regression case. It's an actual number. Whereas classification is I want to predict if an image is a dog or a cat. Is it a 0 or a 1? And that's a classification task. And so depending on the type of task that we have, we use a different loss function for that. And for a regression task, we could use a mean square error. This is what a mean square error is. There's a bunch of different losses. It doesn't really, basically you get these by experimenting which one is the best one. But we also don't really pay attention to the formula because in TensorFlow, this is done for us as well. We just call this function. And same with classification. We might use a binary cross entropy. It's not really important to know what kind of losses, but just know that we use different losses for different types of different types of tasks that we might have.
Can I ask you a question really quick?
Of course.
On the previous slide, I noticed that we didn't specify the activation function for this. So does TensorFlow take care of that, and does it take care of that?
Yeah, absolutely right. Yeah. So we could do the activation function. By default, it's a linear activation function, which kind of means there is no activation function. But basically, in order to do the activation function, we would set dense, and we would set the number of neurons. Let's say I want 16 neurons, comma, the activation. Sorry, it's really hard to write in this, but the activation. And then we would set that equal to whichever activation function we want. And all of those are built in to TensorFlow.
Okay.
Yeah. Does that make sense? Yeah.
Yeah, that makes sense.
We'll actually implement it next time. So this is sort of like an intuitive understanding of what's happening and why. So in order to find those weights though, we have our cost function, but we need to still find those weights. If you guys are familiar, if you guys have taken Calc 1, you guys probably remember that if we want to minimize a function, we take the derivative of that function and set it equal to 0. This is essentially what we're going to do now. We're going to try to minimize our cost function. Remember, we have this loss or a cost function, which is mean squared error or binary cross entropy. And we want to minimize this as low as possible because we want our predicted value to be as close to the value of our actual value. And so we use a technique called gradient descent to do this. And basically the algorithm for this is initially our weights are initialized randomly. So our weights, if you guys remember, which are our slopes, if you guys want to compare it to linear regression, they're initialized at randomly. So it could be 5, it could be 3, it doesn't matter. Those weights are obviously not good enough to get a good general function. We need good weights, so our function is generalized to other input data. And so initially our weights are going to start off at a peak, or they're going to start off essentially at a really bad position. We don't want this. We want our function to be minimized. Remember, because our cost function is our error function. We want our error to be as low as possible. And so we're going to essentially try to minimize this. We start off at a peak, and we try to bring this as close to possible at a global minimum. In practice, this is kind of hard to do because our cost function could become pretty complicated. The more layers we add, the more neurons we add, our cost function becomes multidimensional, which means we could have millions of dimensions. And obviously that's pretty impossible to visualize. And it becomes harder to come up with good weights. But we can do it using gradient descent. And essentially what we do is we loop until convergence. In practice, it's difficult to know when we converge, but let's just say for now, we're in a loop until convergence. Step 3 is we compute the derivative of our error function or our cost function with respect to our weights. You guys remember from Calc 1, let's say we have the function x squared. We want to minimize this function. So we take the derivative of x squared and we get 2x. We can put that to equal to 0. So let me write this actually. We have x squared. We want to minimize this function. So the derivative of this is going to be equal to 2x. We then set this equal to 0, and we see that the position or our data point essentially, or not our data point, the place where our weights are going to be minimized are at 0. And so this is obviously a simplified case, but this is essentially what we're doing. We want to take the derivative of our cost function. If you think of it like Calc 1, our cost function is going to be our x squared. Obviously, it's not because, as I mentioned in the previous slide, our cost function is either a mean squared error or other cost functions. But we take the derivative of that cost function with respect to the weights. And in practice, this is actually also difficult to do. But using TensorFlow, using different frameworks, they have something called automatic differentiation, which means they do this for us. We don't have to worry about differentiating complex functions. And so I'll explain how they do it a little bit, but just know that we don't really care about actually differentiating it because it does it for us. And so the next step is to actually update these weights. We have our original weight, which was initially set at some random value. So our new weight is going to be equal to our old weight times some alpha. I'll explain what that alpha is, multiplied by the derivative of the cost function. This derivative we got in step 3. And I'll explain how we get that derivative in the next slide, or next slide. But we multiply that by this learning rate, or our alpha, and we subtract that by our old weight. Why do we subtract here? Because we want to minimize. If we wanted to maximize, we would add it to our previous weights, but we want to minimize our error. We want our error to be as low as possible. And so we want to minimize this and subtract from our previous weight. Now, I'm going to talk about the learning rate. What is this alpha right here? This alpha is our learning rate, as I mentioned previously. And what this does is obviously multiplied by the derivative of the cost function. But this tells us by how much do we want to move. So you guys are probably in calculus, the derivative is the rate of change. We want to change our weights, right? We're not happy with randomly initialized weights. Our weights are pretty bad right now. We want the best weight. So we want to move those weights to a good minimum. And will we do that? Well, we want to know by how much do we move those weights by. And by how much is our learning rate or our alpha. And this is actually pretty difficult to, not difficult, but it's pretty important to place correctly. Because if you set your learning rate too high, it's going to jump to some global minimum. For example, if we set it too high, it's going to jump very far. And then perhaps it's going to go into, our weights are going to be in a bad position. If we set it too low, our weights might barely change and it might never reach our global minimum, which is what we want. Now, let's say we set our alpha good well, then if we look at this graph, we start off at this peak. It's at a bad position. So in our first iteration, we move down because we can see that this is a better position than prior. And we move down by our learning rate, or our alpha. And this is by how much are we going to move down by. And so as you guys can see, this cost function eventually minimizes to its global minimum. And this is what we want. In this case, our function is going to be generalized. It's going to be a good function. And so to data it's never seen before, it's going to be able to generalize it. So there's a question, what do the peaks represent? Those peaks are essentially our error function. They are our cost function. So if we were to graph our mean squared error, we would get this graph. In practice, we have millions of dimensions, so it's very difficult to graph that and to visualize it. But in a simplified case, this graph is our cost function. And we want to minimize this cost function by moving the weights to a global minimum. Do you guys have any questions?
I was just going to ask if you can find the minimum of the derivative beforehand. Why don't you just set the weight to that in the first place?
That's a great question. Because in practice, our function is pretty complicated. Because if we have many layers, our function becomes, like I kind of explained this before, but we have composite functions. And so we could have millions of weights. We could have, in many cases, hundreds and thousands of weights. And so taking the derivative with respect to each weight becomes very complicated because that's a million-dimensional problem. And so it's pretty much impossible, actually, to find the weights by hand. And so we have to use this gradient descent algorithm, essentially, to find the weights. Does that make sense?
Yeah.
All right. So this is also a pretty good visualization of a simplified function using gradient descent. And of course, in practice, this function is way more complicated than this, but this is a good simplified version of it. As you guys can see, we start off at the top at a bad position, and we go down. In this case, our learning rate is it's set pretty badly, so it doesn't go to our global minimum, which is what we want. In this case, it does go to our global minimum eventually. And the same with this case. It goes to our global minimum, which is what we want. Essentially, at that global minimum, our error rate is low, or as low as it could possibly be. Which means that if we have a prediction and we have our actual, our prediction is going to be very close to our actual. And so there's different gradient descent algorithms. They're all variations of another. It doesn't matter too much, but these are in TensorFlow. These are all the implementations of it. And we'll explore these next time when we actually implement a neural network. And so now I'm going to talk about how do we actually find the derivative, because the derivative is, in practice, pretty hard to find. So this derivative is the derivative of the cost function with respect to the weights. And the way we find that is we take the derivative with respect to, so let's say we want to take the derivative of our first weight. And this is a simplified neural network model. You're not really going to see this in practice, but it is good for understanding. We take the derivative, and also, by the way, if you guys don't really understand this or don't really care, it's okay. The math isn't too important because we have the implementation in TensorFlow. And it does this for us using automatic differentiation. But essentially, to understand this, we take the derivative with respect to our cost function, which is our error function, with respect to our prediction. And then we use the chain rule. We multiply that by the derivative of our prediction multiplied by the first hidden neuron. Then this is, remember, this is a hidden layer. And we can have as many hidden layers as we want and as many hidden neurons as we want. So we take the derivative, in the simplified case, we take the derivative of the prediction with respect to this hidden neuron, and then we multiply that by the derivative of the hidden neuron with respect to the weight. And you just do this for each of the neurons, essentially.
So it's like dynamic programming, right? Like the algorithm. Okay.
Mm-hmm. Yeah. And again, in TensorFlow, this is pretty much implemented for us. In practice, we would just do model.compile, and this kind of initializes it, and during runtime, it differentiates it for us. We choose an optimizer. In the previous slide, I showed a couple optimizers. In this case, we'll use Adam. It doesn't really matter. It all depends on your case scenario. But let's just, for this example, we'll use Adam. And we'll set our learning rate equal to 0.01. This learning rate is our alpha, remember. So this is by how much our derivative is going to move by, how much our weights are going to move by, essentially. And finally, we also initialize our loss. And this depends on the task that we want. And so for this example, we're just using mean squared error, but it depends on the task. So now I'm going to talk about how do you determine the number of layers and the number of neurons. In practice, there's really no formula for this. It kind of just comes by experimentation. So you add another layer and see if the accuracy goes up, or you add some more neurons and see if the accuracy goes up. But it is important to have a good, basically you have to have good number of layers and good number of neurons for your task, for your specific task. Our goal, like I mentioned before, is to have an ideal fit. We want our function to be as good as we want it to be approximated to our data as well as possible. In this case, we see it's kind of curved data. And obviously you can't use linear regression for this because it's not linear. But in this graph, our function is pretty well generalized. If we give it a data point it's never seen before, for example, it's probably never seen this data point, it's going to predict pretty well that it should lie somewhere right here. And it's going to give us this prediction, which in this function will probably be a good prediction. If we use too little neurons or too little layers, we might underfit. Underfitting means that our function hasn't generalized to our data. This might be because our data is too complicated. There might be no relationship between the data and between the input and the output. But essentially, we might underfit and our function might not understand the relationship between our input and our output. And as you guys can see, this is just a linear regression model, and our network is probably too simple. There's probably too little layers that it just predicted it came up with a bad function, essentially. And so if we give it something that's never seen before, like over here, it's not going to do good. It's going to predict right here it's going to predict right here when it should have predicted right here. We also don't want to overfit. And this is more of a problem in neural networks because overfitting is when you have too many layers and too many neurons. And when this happens, your function essentially, your model essentially memorizes data. It tries to fit that function to every single data point. So as you guys can see, this function is trying to just trying to approximate to every single data point it's given. We don't want this because if we give it, again, something it's never seen before, it might predict right here when it should have predicted right here. And this is also in practice, you just have to experiment and find out what's the best number of layers, what's the best number of neurons for your specific task. And so pretty much a summary of all this is we talked about the structure of a neural network. Essentially, we're given an input, we multiply the weights, which is our slope, by our inputs, plus a bias, and then we apply our activation function, which allows us to apply nonlinearity. It applies our function to generalize to nonlinear data, and which gives us our prediction. We could also have more layers, as I talked about. This having more layers allows our function to approximate more complex functions. It allows our neural network to learn complex things. And in the world of complex data, this is needed, and this is why. And actually though, if you have more layers, it also adds to the computational expensivity, which means that the more layers you have, it takes longer because you're doing more calculations. And so it's also a big balance to have as to whether your computer or your GPU can handle the amount of training you have. And again, this is a big reason why neural networks have become so big in this decade, in the few decades, is because in the 1950s, 1960s, they didn't have good computers. They didn't have a lot of data. And this also goes to the limitations of neural networks in that they need a lot of data. They need maybe millions and millions of examples, whereas obviously humans need only a couple. And they also they're very computationally expensive. But this has also given us many breakthroughs. For example, if you go on Netflix, their recommendation system is all machine learning, it's all neural networks. If you say, hey Google, hey Siri, that's all neural networks. They're all variations of neural networks, which we'll talk about in different lectures. They are all basic neural networks, or they're all based off of neural networks. And finally, we talked about training, in which we use gradient descent, in which we want to minimize our error. Initially, our error is going to be pretty high because our weights are initialized randomly. So we want our error to be as low as possible, in which we want to minimize this error. And so we use gradient descent to try to minimize this and try to come up with the best possible weights. So that's pretty much it. Do you guys have any questions?
I have a question.
Go ahead.
So in our training example, how do we tell if we've gotten to a global minimum and not just a local minimum?
That's a great question. Many times we might get stuck in a local minimum. If you see this, that means that the way you see this is that your error might be high, which means that you want your error to be as close to zero as possible. And using TensorFlow, you can see it prints out what your loss is or what your error is. And so you might see that your error is stuck at 0.5. And that happens too, actually. It might get stuck in a local minimum. And so your error might be at 1, which means that you want it to be at 0. But as you keep training, it just doesn't learn. It never goes to 0. And that's one way you can tell that it's stuck in a local minimum. And that might be because it's underfitting. That might be because it's overfitting. But you can also tell by accuracy. If your accuracy isn't going up as you iterate, then that's also a good sign that your network isn't learning and that it might be stuck in a local minimum. But great question, yeah. Does that make sense?
Yeah, that makes sense.
Right. Any other questions?
I guess I have some questions about just like, and if other people have questions about the slides, then I can wait. My questions are more like, how are you planning to continue on with like doing these lecture series and the group projects and things like that?
Yeah, we're gonna have lectures every other Friday, just so it gives me time to build the lectures and everything. Next week, I want to have a practical lab, most likely, in that you guys will actually be able to implement this neural network. And I'll show you guys how to, because we didn't really talk about how to implement it too much. And so we'll talk about it and I'll show you guys how you implement it. And we'll apply that to some real world data. So maybe it'll be like housing, predict the housing price or something like that. But yeah, we'll talk about that next week. Or next other week, yeah.
So are you planning, sorry, you said next week, are you planning next Friday or the Friday after for this?
The every other Friday. So not
every
next
other Friday.
The next Friday.
Okay.
Yeah.
Okay, cool. Yeah, this lecture was really good. I enjoyed it. So thanks.
I'm glad. Also, yeah, my goal kind of is to get everyone on the same level, just so later on in the semester we can do pretty cool, because we can use this. This is the basics, but we can use this for pretty cool applications. And so we'll talk about other variants of this, of deep learning too. But I think we can apply this to pretty cool projects. So, yeah, any other questions?
I have a question.
Mm-hmm.
For the programming, you like to use TensorFlow versus RStudio or Python?
Mm-hmm. So
why is that?
So TensorFlow uses Python. It's a framework essentially. It is Python. It makes it very easy. TensorFlow makes things very easy for us. So for example, we don't have to differentiate. And there's other frameworks, obviously. But for beginners, I found that TensorFlow is kind of the easiest. It's easier to get started. It's easier to learn about it. And in my opinion, it's just easier. Yeah.
Okay. Thanks.
Of course.
Next week, will we go over like what programs or whatnot, or how to implement this on our home system?
Yeah. I'll talk to you guys how to download TensorFlow. There's a bunch of tutorials online, but I'll go through how do you do that. Yeah. And we'll actually program. So we'll download some data and we'll actually program so our model can predict something. Yeah, any other questions? All right, well, that's pretty much it. If you guys have any questions, I'll still be here. Feel free to reach out to me on Discord. I'll be happy to answer any questions. I'll post this recording. I'll also post the slides and also the movie link. I definitely recommend that, the AlphaGo movie for that. And so that's pretty much it. Thank you for coming.
Thank you.
Thanks, Monty.